Hi, welcome to Concept Base. I'm John Hepworth, and this is a Year 11 advanced topic. We are moving into exponential and logarithmic functions, and we're specifically going to be looking at exponential functions. Now, I do want to put a little bit of a preference on this lesson today. The next topic is actually graph transformations. We will do a little bit of graph transformation in here today, and I'll make reference to it, but you'll have a deeper understanding of that when we move into the next topic. So let's look at exponential functions through this question. Explore the function y equals a to the power of x. Find the value of a that results in the tangent to y equals a to the x having a gradient of 1 at the y-intercept. Now, I'm using this question because the syllabus really explores the beginning of exponential functions using this concept of a gradient of a tangent at a y-intercept. So I will fully demonstrate that. But I think there's actually a second way that helps students best grasp that the thing we're looking for is demonstrated. So you'll see that when I do it that way. But do note that you can get questions in this topic in the HSC that relate to this idea of a tangent having a gradient of 1 at the y-intercept. Now, how are we going to go ahead and explore the function y equals a to the x? I could start drawing things, but the best thing to do to explore any type of function is to use some graphical software. The graphical software I'm going to use is DESMOS, and the example I have created looks like this. Now, as always, when I create a DESMOS file like this, I will make that file public and I will share it. So if you want to play around with this file yourself, which you really should if you are learning this concept, then go to the comments and click on the DESMOS link, and then that will bring up this graph for you, and you can have a play around with it the way that I'm going to in this video. So first of all, what have we got here? We've got y equals a to the x as our function at the top, and then a is actually a variable. So I've created a slider here, and you can see what happens to the function as the slider goes smaller. So let's probably talk about that first of all. What's going on here in terms of y equals a to the x? Well, we're just taking a value. Let's take the easiest value we can, 2, and we're just raising it to a power of x. So if we zoom in on the x-axis here a little bit, if we said 2 to the power of 2, we would get 4. So that's what our function is doing. 4 to the power of 2 is going to equal 16 up here. I need to round these decimals off in DESMOS. So that's what this function is doing. It's saying take a number and raise it to the power of the value on the x-axis, and that's the resultant value of the function. Now you'll note here that the graph looks different when the a values are less than 1. Now this is a good concept that comes up again in the future when we're talking about graphing functions. Because sometimes we do things to values that are greater than 1, and sometimes we do them to values that are less than 1. And this particular function that we're doing here, when we're raising it to a power, it actually does different things to values greater than 1 and values less than 1. If you have a value greater than 1 and you raise it to an integer power, then what it's going to do is it's going to increase that value. As you saw, the value 2, as the value of the power got greater, it increased the value of the function. But when you have a value that's less than 1, think about that. If we took the value 0.5 and we squared it, so we times 0.5 by itself, we would get 0.25. So when the a value is less than 1, raising it to a positive power is actually going to make the value smaller. So you get these two different types of exponential functions. One's where the base is greater than 1 and one where it's less than 1. Ones where it's greater than 1, we refer to these as growth functions, and ones where it's less than 1 is usually referred to as a decay function, which will come up in future studies also. All right, so let's just go back to our basic 2 and have a look what else I've got on this DESMOS file here. So then below this, I've done something that we don't know how to do yet. I've done the derivative of that function. And the reason why I've done that is I want to find the gradient of this function at the y-intercept. Now, the y-intercept occurs when x equals 0. So I've said, hey, let's let m equal the value of our gradient function when x is 0. So we can see here that the derivative or the gradient at the y-intercept, which we're talking about this point just here, that the gradient at this point just here is equal to 0.6931. And the syllabus wants us to investigate values of a that will result in that tangent equaling 1. Why is that? Well, you can see that the graph y equals a to the x goes through the value 1. And that makes sense because 1 to the power of anything is always 1. So we're going to have it go through here at 1. And we want to find the gradient being 1 also because we're looking to see when does the derivative function equal the function itself. So the function is equal to 1. So we want to find what do we have to do with a so that the derivative, the tangent to a at this point, is going to also have a gradient of 1. So I'm going to go and turn that tangent on. So it looks like this at the y-intercept there. I might zoom in a little bit more now that we're focusing on this 1 value. And we get this line. Now I've done the line just using the point gradient formula here, where the x value is 0 because that's where we're at, and the y value is 1. So y minus y1 equals m outside of x minus x1, as you will have done in stage 5. And so now we can see that we've got this tangent and we want to investigate when does the gradient of this tangent equal 1. So we move along our A slider until the gradient equals 1. And we get really close. We get here to 0.993, and here we get to 1.02. So we can definitely get very close to it. It would obviously round off and look correct. So with that being the case, let's look at this A value here. It's 2.75. Okay, so it seems like 2.75 or 2.74. I'll try and be precise on the other side. It's not going to let me with the A slider. I got a 2.73 is actually closer here. It looks like our gradient is thereabouts at the 1 value. Okay, that's excellent. So we've identified that there's an A value where the derivative of the function is equal to the function value at that y-intercept. Now, the reason why I don't like this as much as an explanation for students is because you can certainly believe or accept that the derivative of the function here at 1 is equal to 1. But would you believe that the derivative of the function here would be equal to 2? It's really just looking at this unique single position. So I don't like demonstrating exploring y equals a to the x with this tangent idea. What I like to do is I actually like to graph the tangent function. I'm going to change a little bit. Okay, so this purple line that has now appeared is the derivative of y equals a to the x, right? It's the derivative function of that original function. I'm going to turn the line off so there's not too much information on the screen. And look what happens when I move a around. There's a point where the derivative function actually matches the original function exactly. And it's around about at this 2.7 value. So no matter what I do on that function, no matter where I go, when I take the derivative of it, the gradient of the tangent is equal to the function value. Now that's a sentence you really need to be grasping, that the gradient, as in the line tangent that we draw here, is equal to this function value up here. So here, the gradient of that tangent would be 2. Not just the fact that the function value is 2, but the gradient is 2. So we end up with this really strange situation that we haven't seen previously when we were doing derivative functions before, where the derivative function is exactly the same as the function itself. And so the question then is what is this weird number, this 2.7 around about number? Well, it's actually the number E. So E is Euler's number, and Euler's number in this exponential means that when we take the derivative of the exponential, then it's just going to be the exponential function itself. It doesn't change. So therefore, the derivative of y equals e to the x is e to the x. It doesn't change at all. That is the derivative of that function. So if you are being introduced to this concept by this little lesson, then the rule that you're taking away, that was the concept we were after just there. The rule that you are taking away is if y equals e to the x, then the derivative of that is also e to the x. So e, quite a special number, comes up in a multitude of places in mathematics, like pi. It's another one of these irrational numbers that appear throughout mathematics. And for you, it's going to appear in your exponential and log functions. And the special characteristic of it here is that the derivative of e to the x is equal to e to the x.